This conference will now be recorded.
All right, so welcome everyone to another OCP TAP session. This is the 72nd session. Today we have Thomas Rødningen. Thomas Rødningen has been working as an engineer in the time and frequency laboratory at Norwegian Metrology Services since 2020. In 2022, he completed a master in cybernetics from University of Oslo, delivering a thesis focused on evaluating the effect of interference on GPS-based timing devices. Today's talk basically will be about covering some of the activities related to GNSS interference performance at the Norwegian Metrology Service, with a focus on recent activities such as the Jammetest and testing of Galileo OSNMA. So with no further ado, Thomas, the floor is yours.
Oh, yeah, thank you. Let's see.
And also for everyone else, like you can either like put the questions in the chat, or let's see what Thomas prefers. Do you want to have the questions in the middle of your presentation, or you want to have them at the end?
I can probably do some questions in the middle. And,
okay.
Yeah,
so feel free. You can interrupt Thomas if you have a question, or if you want, you can put it in the chat, or we can have at the end the questions. Okay, Thomas.
Yeah, if I'm going to have them in the chat, I just need to find that. But
no, I can help with that.
Okay, thanks. Yeah, so I work with Justervesenet, or the Norwegian Metrology Service, which is the National Metrology Institute in Norway, and we're responsible for the weights and measures. There's approximately 100 employees working, but in the national laboratory we're somewhere between 25 and 30, and with time and frequency we're 3 people working. And our tasks include, well, for the whole metrology service, inspections, certifications, calibrations, legal regulations, and research tasks. The timing laboratory's main task is to generate the Norwegian time, labeled as UTC JV. And by doing that, we also contribute clocks into UTC, and you can see in the graphics here the Norwegian flag's been highlighted, and it shows our clocks. I'm not sure which year this one was made, but right now we're not doing 4 clocks, we're doing 3, but we're getting the one back up again. And besides that, we also do some research and development in secure network timing and the GNSS interference. Where the main activities has been the COSIC time project with Statnett, and lately we've done a test with Galileo OSNMA, funded by the Norwegian Space Agency. And this is just a plot to show we made some changes to our generation of UTC JV last year, and you can see after the change we're now aiming to stay within 10 nanoseconds of UTC, and previously we were quite a bit off from that. When it comes to PNT, we've had contributions to several national initiatives. Back in 2013, we had contributions to a vulnerability assessment, and in 2018 there was the Norwegian PNT strategy, which we contributed to, and lately it's been last 2 years Jammetest, with both 2021 and 22, which is possibly the world's largest open GNSS interference test. And We've done some R&D on PNT security. There's my master's thesis. There's another master thesis which was based around building a spoof-proof GPS clock, and also work within the COSEC time project with Statnet and an EU project called Digital IT, as well as the OSNMA testing. Well, just quickly, but I'm assuming you know this, that it's difficult to protect the GNSS signals. They're weak, unencrypted signals with a well-known code structure, easy to generate new signals, and in most cases you would need to have an antenna outdoors to actually receive the signals. And jamming, well, intentional or unintentional RF noise that may block or degrade GNSS PNT solutions of affected receivers. I've chosen to highlight degrade because it's not something everyone thinks about, but I've got a few examples of what can actually happen. And the spoofing, there's several ways of classifying it, but whether you're doing like incoherent, coherent spoofing, or you classify it some other way, you're trying to mimic the live sky signals. And then you've got meaconing, which is just a rebroadcast of the actual signals, which may cause timing and position errors. And here's an example from the work from my thesis that shows the effect of signal degradation and what can actually happen. If you look at the bottom plot, you can see the number of satellites in use and the visible number of satellites, and you can see that at 1038 or so you get a drop in the number of visible satellites. And looking at the timing plot, there's not really much happening. And so it would assume the time server is actually handling this fine. This is multi-reference time server I forgot to mention, which is fed with external PPS and PTP in addition to the GNSS signal it's seeing. But you can see as we're getting closer to 1045 that it's trying to use some of the satellites again, but it's not quite getting a fix. And coming up on 1046, you can see a huge change in timing for the two external sources, which is a bit of a lie because it is actually the degraded GNSS signals. The other two signals are coming from our lab and are known to be stable. And so you can see you suddenly get a change of more than 30 microseconds without the time server actually saying something is wrong, and it just keeps going with the GNSS source, even though that is the one that is actually failing. And we get to Jammetest, and it's been 2 years with this now. The third one is coming up. The first one was a smaller event done in Skibotn, while the last year and this year it's going to be on Andøya. It is a collaboration between the Norwegian Public Roads Administration, Norwegian Defence Research Establishment, National Communication Authorities, and the Norwegian Metrology Service. It is an open event where interested parties can bring their own equipment to evaluate performance against the GNSS interference that is transmitted by the organizers. There is a limited number of places to this event, and last year I think it was around 100 participants, and it will be somewhere in that same region this year. The actual location on Andøya is based around the village of Bleik, which sits on the map. You can see the red circle for the approximate area on the map, but the main benefit here is the village is surrounded by mountains on 3 sides, and on the last side you got to see, and that's about it. So even if you're transmitting with fairly high signal strength, you're not actually disturbing a lot of things in the area, such as the airport on the other side of the mountain. Yeah. Jammetest 2022 was a week of testing where there were 3 days dedicated to jamming scenarios, both using a high-powered jammer and a selection of smaller handheld devices. We spent 1 day doing spoofing, both simpler non-coherent scenarios and coherent scenarios, some of them mostly related to timing, some mostly related to position. And the last day was used for repeats of previous scenarios and some requests for new things. And I spent my time with the GNSS simulator for this. It was fairly new equipment for us at that point in time, so I didn't have much time to look at other equipment, but we got a few observations from some units we brought with us. And as a general statement, the ordinary GNSS clocks did not handle jamming very well, and spoofing was not handled well at all. We got problems with some clocks stuck up in the mountains and so on. We also had a GNSS firewall with us, and that one correctly alerted to all interference, and it looked absolutely fine. But I was going to redo some tests in the lab afterwards, and I hooked it up, and it had picked up on some issues. But these things have since been fixed in a new firmware update, according to the manufacturer. I just put in the transmission plan from last year. Here you can see how it was spread out, with Monday and Tuesday being spent with jammer, with everyone in the same location really, and the jammer static, and all the vehicles and so on attending also parked. And on Wednesday they were driving while jamming, both with the stationary jammers and with jammers in the actual vehicles. Thursday was spent spoofing, with the fundamental spoofing attacks, or incoherent really, was done before lunch, and after lunch we were doing coherent attacks and also some more timing specific attacks, while Friday was mostly repeat of some spoofing scenarios. The actual test of the spoofing plan I just put in more for completeness sake. I'm not going to actually go through it. There are combinations of false positions times true or simulated ephemeris data and initial jamming. If you want to read it in detail, the slides will be available later. And the Jammetest 2023, which is coming up, is going to be 18th to the 22nd of September. And there's some changes to the plans from last year. We're this year doing 2 days of jamming and 2 days of spoofing. But there's also going to be multiple locations in the area, so that you can run high-powered jamming in the main area, and then you can still do testing with the small handheld jammers down in 2 other areas. The exact plans for what we're going to do spoofing-wise isn't set yet. We're going to be doing a lot of the things from last year, and we have to see if we can come up with something else that would be interesting. Just overview of the transmission plan with the 3 sites and how it's planned out. Here you have the first day with high effect jamming. Second day will be both high effect jamming and some multi-jammer scenarios. Wednesday will be from the main area spoofing and meaconing, but mainly a focus on position and navigation systems, while Thursday will be mostly focused on timing attacks. I've got another example here. This is from the first Jammetest in Skibotn, where we had another of these degradation of signal events, which is, in this case, the jamming transmission was started with low signal strength, but the jammer, the transmission was set at 0.1 watts, but applied 100 dB of attenuation in the beginning, and then the attenuation was gradually decreased to see at what level various receivers actually reacted. During this test, I had a GNSS timing receiver as well as a multi-reference time server with me, but the time server having an external PPS from a chip scale atomic clock as a backup source. And you can see in plot C, as the attenuation is decreased, that in plot D, the actual number of satellites in use are dropping. And when you're getting about 935, there is a change because it doesn't really generate the correct solution anymore. And this time, the time server seems to handle it fine. The timing output it measures from the receiver internal to the time server is just at a static value, which means it's just running on internal time relay. It doesn't see any signal to measure. But the GNSS timing receiver, which I had connected as well, you can see the timing is going off very badly, and it actually jumps up to about 400 milliseconds of a fault, and then it also settles on a frequency offset of about 10 to the minus third, so a rather nasty drift. This is once again signal degradation, and as the signal strength increases, you do eventually get a proper drop, and it just stops providing a solution. But looking at the timing, it would seem the time server got away working fine, but the position plots, latitude, longitude on the left side here shows a slightly different story. It does indicate that there was a position change, and I've plotted that in the map over on the right side, and it did turn out that it actually moved a couple hundred meters. And this is also from 2021, but an incoherent spoofing attack where no efforts made at syncing it. It was transmitting it for a position several hundred kilometers away and about 12 days back in time. And so you can see the time server is clearly reporting signal available, is master is locked, and with an offset between the GNSS receiver it uses and its internal time scale of minus 66 hours. But that isn't right either, because that's just some kind of overflow. It did actually change the time to jump back 12 days. The error in milliseconds you see on the PPS in, that one's probably just due to the phase of the oscillator in the SDR that was used to transmit the spoofing signals. Once again, the PPS signal should be stable. And some more plots of this where you can actually see a bit more what's happening. And if you look at the timing offsets, the PPS of the time server input in the just dwarfs everything in the first plot, and it just so it's been zoomed in, and you see it's not measuring the actual timing on the GNSS receiver inside the time server, but it is still using that data. So I'm not sure why it's actually prioritizing that and is willing to use a solution that it clearly isn't happy with. And you can see the position jump, and also in the plot E, the steering value for the internal oscillator in the time server. What can be noted here is that for this attack, the freestanding timing receiver that we were using was configured for both GLONASS G1 and GPS L1CA, and that kept going just fine. There was no position or timing errors on it at all. It actually managed to utilize GLONASS to keep going even when GPS changed. And then we got what we've spent most of the autumn and winter on after the Jammetest, which is testing Galileo OSNMA. These were lab tests, so where we mixed real signals with simulated signals to see how our timing receivers actually would react to pole signals and whether OSNMA would trigger it correctly. And we had two receivers operating in different modes. It's the same model receiver. One operating what we've called a pure OSNMA mode, where it would only use actual authenticated satellites, while the second receiver sits in a hybrid mode where it will use authenticated satellites or satellites with status unknown, which does help you in the way that you can actually do multi-constellation GPS, Galileo, GLONASS at the same time, but there are some weaknesses in such an approach that you need to be aware about. And an important thing to note here is that the receivers were tested more or less as is. We've not made any efforts in tuning the regular interference detection methods that are integrated in it. They've just been left on, and we've looked at results, but it might be possible to get better performance out of this through some configuration. And what we've been aiming for really is to perform synchronized spoofing while manipulating Galileo and GPS parameters. We've done tests both with position and time changes, but what we've found was quite effective was manipulating the UTC timing parameters that is transmitted. And doing this, you're not actually changing the navigation solution. You're not really doing anything to the internal timing of the receiver. You're just altering how it would calculate what is UTC supposed to be according to the satellites I'm receiving. And some of the parameters are, well, the parameters we manipulated are in the figure below here, where you got A0, which is basically a offset between UTC and the system time of the GNSS system. A1's a drift parameter to show how they change in relation to each other, and then you got the fields which are marked with LS, which are related to the leap seconds, which is actually quite important. You've got the current leap second, future leap second, and leap second event. And we'll get back to those soon. First, we did some baseline tests where we ran a spoofed GPS and Galileo signal, but with as close to real data as we could actually get. I was a bit off with the time sync in this one. As you can see, there is about 20 nanoseconds off from what it should be. You can see here that initial both receivers are taking the signals from the antenna and being absolutely happy. You get into the blue area, we're actually transmitting spoofing signals. And you can see the receiver in pure mode quickly detects something going on and just shuts off the solution. You can see that it is the OSNMA spoofing that is flagging it. If the generic spoofing detection built in isn't saying anything, the RAIM test integrity testing is just going to inactive because there's no solution. And the PVT solution is just giving an error with no measurements. The hybrid receiver, on the other hand, is a bit of a different story. You can see it is passing the RAIM integrity checks. There's no PVT solution error reported. The generic spoofing detection is saying spoofing's unlikely, but the OSNMA spoofing is still going up, flagging that there's something not right here. Running another test here is actually we're on GPS and Galileo UTC timing parameters. At this point, we actually changed the number of leap seconds. And you can see here, you've got 2 plots for each receiver. You got the delta T leap second, which is the information it is receiving from the satellite signals. And then you got trusted time delta, which is an offset between the GNSS receiver's time and time as observed from one of our NTP servers. So not good for very small things, but for leap seconds, it gives a good indication of what's actually happening. And you can see in the pure OSNMA mode, it is receiving, the blue plot is showing Galileo, the red one's GPS. You can see it is receiving the invalid leap seconds from Galileo. I don't have all the plots, but it did flag that it was being spoofed and all of that, the same as the previous one. But the interesting thing here is that you see after, is it 17 minutes or so, 15, 17 minutes, it is actually implementing the invalid leap second, even though it isn't actually getting a PVT solution at all. And if you look at it, it actually implements it when it receives information from GPS, not when it comes in from the Galileo system, which is a bit of a weird thing to happen, considering you're not supposed to be using GPS at all. And in the hybrid mode, the story is similar. You can see the information's getting into the receiver quicker with Galileo because it's sent more often, but it doesn't implement it until it gets it from GPS. So there are some problems here, and the hybrid mode receiver also flagged OSNMA here, but the other spoofing was still fine.
Can I interrupt you very briefly then? As this is a test you've conducted with one specific receiver, right? You're not saying that
Yes.
this applies to all receivers.
No, this is for one specific receiver that we tested on. But it shows you need to actually be careful with, even though you think it's done right, it's not necessarily done the right way. And
okay.
Yeah.
Okay, thank you.
So what we're seeing here is then some weird behavior from the receivers, but you would expect receivers to not actually implement this kind of information when you have indications that there's something wrong with the received signals, but that's how it is at this point, at least. We also did some other timing parameter tests where we set the drift parameter on only GPS to 300,000 femtoseconds per second, which is the absolute maximum value you can set it, at least for L1CA. And you can see in the pure mode, it's doing fine. It's not really being affected by it. It's just doing its thing here, seeing as we're not spoofing anything Galileo related, we're just spoofing GPS. But you can see the hybrid receiver is running off a bit. You can see in the XPPS offset here that it is drifting off and then trying to correct itself, correcting itself over and over again. And the clock by is also affected, but not severely. And the main thing here is that OSNMA has and Galileo has the tools to actually alleviate this problem, because Galileo transmits its own offsets, but it also transmits the offsets between Galileo system time and GPS system time. And using that, you can take the data from an authenticated Galileo satellite and then just go say, this GPS satellite, this isn't right. But that is probably something for the future. We've also had some observation. This is for a lot of the tests still receiver specific, that the OSNMA mode will run, say, spoofing detected for about 10 minutes, and then it will go to no spoofing detected. And digging a bit more into that, you will see in the hybrid mode receiver that the actual OSNMA status at the time that change is occurring goes from authenticating to initializing, which is happening because the spoofed signals we are transmitting do not contain any Galileo OSNMA data. It transmits what the receiver expects from a satellite without OSNMA enabled, so just a string of zeros, which our theory is that after about 10 minutes, the information stored in the receiver about which satellites are actually active with OSNMA is simply overwritten by the invalid data, so you don't have the means to actually verify whether the satellites are authenticated or not yet. And this is also something that is probably receiver specific, but it is an interesting observation and something to be aware of, that even though the spoofing detection goes down, is the spoofing actually down, or did the status of the service change? So I've just grabbed the conclusions that we used for the OSNMA final workshop in the presentation there. And say OSNMA is, at least for what we've been doing, a powerful anti-spoofing tool. It detects a lot of attacks that haven't been actually detected by conventional means of integrity checks. And every time we spoofed Galileo, it raised the flags. And among the observations we did here is that you should actually regard Galileo navigation data as inauthentic if the authentication fails for at least some of them. Seeing as all satellites aren't active with OSNMA at all times, you shouldn't be using those if you see some satellites being spoofed. Assume that everything you see is. And it would be beneficial if you could keep updated information on which satellites can actually be authenticated in a way so that it doesn't actually expire after 10 minutes. And of course, the pure mode should not use any GPS data at all, but receiver error. And leap second information, that is something that you need to be really careful about, because receivers seems to accept it. And not just from this test, but from other tests we've done as well with different units. And leap seconds is something that seems to be accepted, both positive and negative, small and large jumps. Not really. Receivers aren't really too fussy about that. If it comes from what seems like a valid signal, we trust it. And just opportunities for cross-validation, both within Galileo satellites and also between Galileo and GPS. And certainly to be safe, you need to combine OSNMA with other ways of integrity measures, such as checking RF signals, verifying navigation data, and PVT solutions. But through some projects, we've looked at things that should be possible to use as countermeasures. This one's an example from one of the COSIC time projects, where you had a time server with multiple reference. It had PTP, it had a cesium clock directly, it had a rubidium clock, and it had GNSS. And what happens when there is a fault with the main source? It doesn't shut off, but the quality is severely degraded. So the cesium clock stops being a cesium clock effectively and turned into an OCXO. How does a multi-reference system actually handle that? It would seem it still trusts its main source, and you can see here it's reporting the main source PTP as fine and stable, and all the other sources connected directly to it are actually drifting off over the span of a couple of hours. And so we think there should be some more logic to these kind of units than just, this is my main priority, I use that one until it stops. You should have some kind of sanity checks on it, that if several other sources drift off, it's probably something wrong with the main one. Other countermeasures that are in use are the firewall and integrated firewall-like systems which does signal analysis and have a lot of detection rules that they work on. And those are fine. A lot of the time they detect what's going on, they tell you, but they're still very much closed boxes. You don't know what they're actually checking. You don't know what they're doing at all. And you don't know how it's been tested either, and what vulnerabilities it will actually protect against, which I find as kind of problematic. And yeah, we got just a quick summary of some lessons on what we've been seeing. That in the physical layer, improved antennas suppress signal from ground is the easiest thing you can actually do. And it also helps you can run systems with multiple antennas, that kind of thing. And but in signal processing and authentication, as a general rule, receivers shouldn't be as naive as they are today. A lot of the time they see a signal, they implement it, and the strongest signal wins, at least if they're kind of similar to begin with. And also, as you can see with signal degradation errors, that every available signal isn't necessarily suitable. Sometimes it is better to go to holdover. And this also builds in with like more system integration and how units integrating GNSS receivers really shouldn't blindly trust the information coming from the receiver, particularly not if you have several sources available, because a single failure should really not be critical in a multi-reference system. And as we have seen with Jammetest, that testing is important, also independent testing. And no system is perfect, even systems designed to protect against GNSS interference have their inherent flaws. And that's it for me. Thank you.
Wonderful. So let's open up the floor for some questions then.
Yeah, I mean, I would just mention that as it relates to the TimeCat which is really sort of what we have focused around in this group, isn't it? Previously, Septentrio gave a presentation which specifically deals with sort of the resilience to spoofing and jamming, and we've just made a deal with them to bring their Mosaic T chip to the TimeCat and an RCB, and it'd be really interesting to test, this in these conditions, because I believe that a lot of the things you experience, let's say, hinges on a specific GNSS receiver, right? So your mileage may vary very considerably.
I think that's a good point. I mean, in general, it would be good, like, to expand this experiments on a variety of GNSS or combinations or.
Yeah, it certainly would be interesting to run tests on several receivers and compare how they perform, and also various combination of which signals are being tracked. And that is a question about funding and time, really, on our part at least.
So, like, I don't know, maybe I missed it in the presentation. How is it, like, let's say, with different bands? Let's say if you have L1, L2, L5, like, simultaneously, like, are you affecting all five, or all three?
That's been different for between some of the tests. For the OSNMA tests, we were running spoofing on GPS L1, L2, L5, Galileo E1, E5. And for some of them, we were only doing GPS and so on. But there's certainly other combinations to try there as well. And for Jammetest, we only had licenses to simulate GPS L1 and Galileo E1. So we were limited there.
Yeah. Okay, makes sense.
And I guess it's also worth mentioning that whereas Galileo is currently the only system that has a message authentication built in, if you look at something like the Fugro Atomicron service, okay, it's a subscription service, but it provides essentially NMA for every constellation. So this can also okay, so that today is only supported in the Mosaic T chip. Again, which we are bringing to the timecast, but in the future, that will be supported. They plan more widely, and so this should also really help solve some of those problems you mentioned.
Yeah, wonderful. All right, any more questions? If not, we can give you back 10 minutes. Okay, great. So we'll see everyone in 2 weeks then. All right, bye everyone.